Okay, in this video we're going to be looking at L'Hopital's rule. This section is in Chapter 4 of the Calculus Volume 1 book. I don't remember exactly which section it is. I think it's 4.7, 4.8. But we do need it for the improper integrals, which is the next section we're going to look at. To give you a little idea of kind of a sketch of the proof of L'Hopital's rule, the first thing we're going to look at is what's called Cochise's extended mean value theorem, which says to suppose f and g are differentiable on the open interval AB and continuous on the closed interval AB, and g prime of x is not equal to 0 for all x in AB. Then there exists a c in the open interval AB such that f prime of c over g prime of c is equal to f of b minus f of a all over g of b minus g of a. So kind of an idea of the proof is we're going to put h of x to be equal to g of x times f of b minus f of a minus f of x times g of b minus g of a. Note h is continuous on the closed interval AB and differentiable on the open interval AB, because it consists of scalar multiples of g of x and f of x, which were already continuous on the closed interval and differentiable on the open interval. If we evaluate the function h at a, it's going to be equal to g of a times f of b minus f of a times g of b. And if we evaluate the function at h of b, then we have this is equal to g of a f of b minus f of a times g of b. And so this is Rolle's theorem applies, and what Rolle's theorem applies is what Rolle's theorem says is if we have a function that's continuous on closed interval, differentiable on the open interval, and the endpoints outputs are the same, then you have to have a horizontal tangent. So you have to have a horizontal tangent somewhere. Whether your function is constant or flat, you're going to have a horizontal tangent somewhere. So Rolle's theorem applies, so there exists a c in the open interval AB such that h prime of c is equal to 0. That's our horizontal tangent. Thus, the derivative of h of x at c would be g prime of c, f of b minus f of a, minus f prime of c, g of b minus g of a. So if we go ahead and solve for f prime of c over g prime of c, that's going to be equal to f of b minus f of a all over g of b minus g of a. And this is an example of Cochise's extended mean value theorem. So we're going to go on to the next slide. Oops, did I go too far? Okay. All right, so we're going to look at L'Hopital's rule, kind of an idea of the proof. So we're going to suppose that f and g are differentiable on the open interval AB, containing c except possibly at c itself. Suppose that g prime of x is not equal to 0 for all x in AB, except possibly at c itself. If the limit of f of x over g of x as x approaches c produces the indeterminate form of 0 over 0, then if the limit as x approaches c of f prime of x over g prime of x exists or is infinite, then the limit as x approaches c of f of x over g of x is equal to the limit of x as x approaches c of f prime of x over g prime of x. That's your L'Hopital's rule right there. Okay. So we're going to assume that our original function f over g as x approaches c has a indeterminate form of 0 over 0. And we'll go ahead and suppose that the limit as x approaches c of f prime of x over g prime of x is equal to a, where a is a finite value. Let n be a real number such that a is less than n, or n is greater than a. Okay, and then let r be any number between a and n. Okay, so there's n, there's r, and then there's a. Since the limit as x approaches c of f prime of x over g prime of x is equal to a, there exists an x naught in the interval c to b such that f prime of x over g prime of x must be less than r, because we're going to be approaching a at some point in time. We have to be less than r, so we have to be down here. and that's going to occur for all x in the interval c to x naught. Let x and y be elements of c comma x naught, such that c is less than x, and x is less than y, and y is less than x naught. Okay, now the Cochise mean value theorem applies to this interval xy, and so there exists a t in x comma y, such that f of x minus f of y over g of x minus g of y is equal to f prime of t minus g prime of t. Now, if we let x equal to 0, we know that both f of x and g of x are going to go to 0, so you're going to have negative f of y over negative g of y, or just f of y over g of y. Now, that's going to be less than or equal to r, and when we get the limit, it's possible it'll be less than or equal to r, which is strictly less than n. So any particular n greater than a, we have shown that the limit of f of y over g of y is going to be less than n. And then we're going to pick any number less than a and show that the limit is going to be greater than that. And so this process will show that it's going to have to be a. So going on to the next page. Now let m be a real number such that m is less than a. And r a real number such that r is between m and a. Since the limit as x approaches c of f prime of x over g prime of x equals a, there exists an x naught in CB such that at some point in time f prime of x over g prime of x must be greater than r, so you're going to be up here somewhere, for all x in this interval c to x naught. Let x and y be in the interval c to x naught such that c is less than x, and x is less than y, and y is less than x naught. And apply Cauchy's mean value theorem. There exists a t in x y such that f of x minus f of y over g of x minus g of y is equal to f prime of t over g prime of t, and that's going to be strictly greater than r. If we let x approach c, by assumption, f of x and g of x are going to go to 0. So then we have minus f of y over minus g of y is going to be greater than or equal to r, which is strictly greater than m. Okay, so what we've done is we have a here, okay, and we pick whatever number we want. We pick an n, and we show that the limit has to be less than n. And m, anything below it, we show that that has to be greater than m. And what we can do is we can keep getting closer and closer to a from above and below, and that is kind of the idea of squeezing the limit to be, it has to be a. Thus, and so I've proved the case where we're approaching from the positive side. The negative side is similar. So, well, it's more of a sketch. I wouldn't call it a proof. It's just kind of an idea of the proof, really. Thus, the limit as x approaches c of f of x over g of x from the c approaching the positive, x approaching c of the positive side, is equal to the limit as x approaches c from the positive side of f prime of x over g prime of x, and that's going to be equal to a. This can be extended to left-sided, two-sided, and limits at infinity. This can also be extended to other indeterminate forms, such as plus and minus infinity over plus and minus infinity. Some of the indeterminate forms, 0 over 0 and plus and minus infinity over plus and minus infinity, you can just straight up use L'Hopital's rule with those. Okay? If you have 0 times infinity, 1 times infinity, 0 to the 0, infinity minus infinity, or infinity to the 0, these all need some algebra. And you're going to use algebra to rewrite as a 0 over 0 or a plus and minus infinity over plus and minus infinity. Okay, and we'll do some examples. Probably in this video they'll be fairly basic. They'll be the 0 over 0 or the infinity over infinity types. So let's go ahead and run through a couple examples. So number 1, we have the limit as x approaches negative 1 of 2x squared minus 2 over x plus 1 First thing with limits is try to directly substitute. When we try to directly substitute, we get 0 over 0, and that's indeterminate. So this is exactly what L'Hopital's rule says we can do. We can take the derivative of the numerator and the denominator. Be careful that we're not actually using the quotient rule. We're just taking the derivative of the numerator and the denominator. And so this becomes 4x over 1, and now we can directly substitute, and our limit is -4. Okay. Now let's look at the limit as x approaches infinity of 3x squared minus 1 over 2x squared plus 1. If we imagine plugging in a large number, we're going to have essentially an infinity over infinity. So this is a candidate for L'Hopital's rule. So limit as x approaches infinity of 6x over 4x. We can go ahead and reduce, and that's the limit as x approaches infinity of 3 over 2, and it is just 3 over 2. That's the limit. Okay. All right, let's take a look at the limit as x approaches 0 of x to the 2x minus 1 over x e to the x minus 1. If we try to directly substitute in, we're going to get 1 minus 1 over 1 minus 1. So because e to the 2 times 0 and e to the 0, those are both 1. So we get the indeterminate form 0 over 0. So we apply L'Hopital's rule. So limit as x approaches 0 of 2e to the 2x over e to the x. Okay, and then we can go ahead and directly substitute now. So we're going to have 2e to the 2 times 0 over e to the 0. So it's going to be 2. Okay. All right. Let's go ahead and look at a couple more examples. Let's look at the limit as x approaches 0 of e to the 2x minus 1 over x. Again, this is of the 0 over 0 variety. So we'll go ahead and take the derivative of the top and the bottom. So limit as x approaches 0 of 2e to the x. Go ahead, directly substitute. Just get 2. Alrighty. Now let's suppose that a and b are not 0. Then the limit as x approaches 0 of the sine of a, x, over the cosine of, over the sine of bx, excuse me. And that's going to be the form 0 over 0, sine of 0 is 0. So this is going to be the limit as x approaches 0 of a cosine ax plus b cosine bx, which can be a cosine of a times 0 over b cosine of b times 0. Cosine of 0 is 1, so this is going to be a over b. Okay, I think we got one more here. Limit as x approaches infinity of 4x e to the negative 2x, 2 over x, pardon me, minus 4x. So x is going to infinity, so 4 times infinity is basically infinity. And we have e to the negative 2 over almost infinity. So it's going to be basically e to the 0. And e to the 0 is going to be 1, not 0, excuse me. So that'll be infinity times 1 minus infinity. And so that's an indeterminate form. So we're going to go ahead and factor out a 4x. E to the negative 2x minus 1. Okay, so that's going to be, this time it's going to be infinity times 0, because we're going to have essentially e to the 0 minus 1. Okay, and then we're going to do a little bit of trick here. We're going to go ahead and write x as 1 over x. Okay, so that x there we're going to write as 1 over x. All right, so this is going to be the limit as x goes to infinity of 4 times e to the negative 2 over x minus 1 over 1 over x. And now this is going to be 0 over 0. And now we can apply L'Hopital's rule. So limit as x approaches infinity of 4 e to the negative 2 over x times 2 over x squared by the chain rule, all over negative 1 over x squared, is equal to the limit as x goes to infinity of negative 8 e to the negative 2 over x. Now we can go ahead and evaluate this. So the x is going to get very large. So negative 2 over a large number is going to be very small, essentially 0. So e to the 0 is going to be 1, and so we're left with negative 8. Okay. So stay tuned for the next video on L'Hopital's rule. We'll do a couple more examples, and we'll see you next time.